And hello, welcome everyone to this video. So I'm going to be talking about MATLAB today and run you through at least one full cycle of turning some time response input and output data into a sort of a frequency response based transfer function. Okay, so I think in the last few videos I've explained how some of these scripts work, like the fast Fourier transform, the gain and phase bits. Okay, of course also I took some time to explain what this peak finder was about, and this is a very important script because it helps us to find the relevant input frequencies that we want to test our system at. Okay, so basically now what I have for you is a batch of sample data. Okay, so this is the input, this column here is the input, this column here is the output, and what we are going to do is to try and do some frequency response on it. So I just run you through the basic things. Okay, first thing, you're going to output an array, okay, a frequency array of frequency data. Okay, and next thing is what you're gonna have is this column 2 here will be your input, column 3 here will be your output, the fast Fourier transform of such. Okay, gain and phase is here. Okay, you can see the relative gains and the phases over here. Okay, the gains and the phase shift. Okay, so all of these are plotted so-called for you. And then next thing here is the peak finder code, and this is important because again helps you to identify the peaks and the inputs and the outputs. Okay, so that you can have a batch of frequency response data containing at various frequencies what is the complex gain, so to speak. Okay, so for example, like this, complex gain CSV and peak frequency CSV. Okay, what am I talking about here? Okay, so so at certain frequencies, as okay, let me show you what the data looks like in the Fourier the frequency domain first. So remember, I have time domain data. This is time domain data using a PRBS or pseudo random binary sequence, which means I'm testing multiple frequencies at once. That's basically the long and short of it. I actually had a lab view. Okay, so anyway, I'm back from a long break. Very long break. Kind of fast forward the thing, but yes, I was actually doing this pseudo random binary sequence data. Now I have time data, I need to convert that into frequency response data. So what I plot is the input and output of the Fourier transforms and try to find the peaks. Okay, so let's just do that first. Okay, I'm going to show you this is what the inputs and outputs look like. As you can see, there are many peaks. Okay, in fact so many that it's easy to lose count. Okay, so we need to kind of understand, what are the important peaks for us to find. All right, so picture this. There's the time domain data, and in the Fourier transform it looks like this. And what we want at the end of the day for frequency response data is a group of vectors. Okay, a group of vectors. First one is like frequencies. Then you'll have a complex gain here. Okay, complex gain. And what is this complex gain talking about? Okay, complex gain is basically something, like I have the Fourier transform of the output over the Fourier transform of the input. Okay, so this is what I like to call complex gain. I like to call it complex gain because it's a complex number. So let's see. Yeah, so what do we have? Yeah, complex gain is this. This is actually the ratio of the Fourier transform of the output to the Fourier transform of the input. Now this is actually a complex number. Okay, so there's a gain and a phase shift, all the data is being captured in there. And where do you take note of this data? You actually take note of it at the peak frequencies. Okay, i.e. to say you want to only capture all of this data at your relevant input frequencies. Okay, so what are the relevant input frequencies? Now it's a little bit hard to see it from the decibel based graph because there are just so many peaks. Okay, one clue we can say, what's in a multi-frequency input data. Of course, for one frequency you only look for one input peak, and it's very easy to find where your data should be. But what if you have multiple peaks? Okay, so what is commonly done, I believe, is to look for the maximum peak. Okay, the maximum peak height here is about -4 to -4.5 decibels. Okay, so -4 to -4.5 decibels. I think that's about it. Now the thing is that it's a lot easier to see what's the relative peak height when you don't use decibels, and you want to use you probably want to use something a little more absolute, so that if you want to find your local maxima, you should only look at the peaks of a certain absolute height. Okay, why are we doing that? Okay, because we want let's say if your maximum peak height is of maybe 10 units. Okay, maybe your threshold is for input signals. Okay, for the input signals your peak height is maybe 10 units. I don't know what that is in decibels, but or maybe that's 1 dB, right? 1 dB or half a dB, 2 dB, whichever it is. But yeah, so that's 10 units. But if you make it such that it is, what are you looking for? What am I looking for? Shucks, I lost my train of thought. How do you know which frequency which input frequencies are noise and which input frequencies are so-called strong enough so that they overpower the noise, so that you have a strong signal to noise ratio? Okay, if you want that, you take your maximum frequency, the frequency with the maximum amplitude, and probably you only take frequencies that are all the way like half. Okay, let me draw it for you. It's a little bit difficult to explain abstractly. So let's say you have amplitude versus frequency, right? So your input frequencies can be sort of randomly distributed if you use a multi-frequency signal. Alright, if you use a multi-frequency signal, maybe you have a frequency graph like that, just like what you saw in this graph, right? In this graph, there's so many frequencies, it's very hard to take note. But what then are the frequencies you want to pay attention to? Because there's so many peaks here, you can actually do the ratio of the fast Fourier transform for each of these peaks, and then you get all the frequency data, response data. However, you might want to neglect some of the lower peaks. Okay, you want to neglect some of the lower peaks. Okay, why? Okay, neglect lower peaks, because if you had noise that is on this level, okay, you have noise that's on this level, and you can see that for lower peaks, the signal to noise ratio is not very good. However, for maybe peaks such as these, the high peaks, right? The high peaks, the signal to noise ratio is good. Signal to noise is good. Okay, you have the signal, the input signal at that frequency is very high compared to the noise. So that's kind of why you want to you only capture the high peaks. So where's the noise here? So if you take a look, I mean, the noise can be considered, in this range minus 35 dB. It's very, very hard to see. But once you take a look at this, you would easily see, the noise is at maybe a minus 35 dB threshold. Okay, the rest is maybe at minus 20 dB. But in absolute terms, the absolute number between minus 20 dB and minus 35 dB is not a lot. Okay, in terms of, the error can fluctuate. Okay, it means that the noise can be the minus 35 dB or minus 20 dB. It's very hard to tell. Okay, but how then do you tell? Okay, from this graph you can try and take maybe anything above minus 10 dB. Those are the input signals you might want to consider. Okay, but like I said before, maybe the threshold you want to consider to find out which peaks you want to consider for your frequency response data. You take your maximum peak as your reference point. Okay, max peak, and then maybe you divide it by half. Okay, you divide it by 2 to get your peak data. Okay, so this will not do for decibels, but it may do better for, let's say, maybe an absolute scale rather than a decibel scale. So let's try doing an absolute scale peak finder, so that we can try and get a frequency response data. So let's do linear peak finder, not linear peak finger, linear peak finder. Alright, so let's do this linear peak finder. We'll call this function linear peak finder. Okay, so the frequency data is all of this. Okay, and I want the input and output to be in absolute scale, Okay. So we'll call this input magnitude. Okay, input magnitude is just the absolute value of the input, and we'll give this output magnitude. Output magnitude. That will be also alright, I'm going to change all the output dB to output magnitude. So input magnitude is the absolute value of the input, output magnitude is the absolute value of the output. Okay, so that's I will not convert the peak to decibels. I'll do find the magnitude of the peaks. Alright, and what is next? I want to calculate my threshold, and remember, my threshold is not based on decibels anymore. For this case, I want to change the threshold to maybe the magnitude of the input divided by 2. Okay, or the maximum value of the input magnitude, and I divide it by 2. So let's have the maximum value of the input and output first. Okay, and divide by 2. Okay, so next step is to calculate our input and output peaks and frequencies. So let's see. Maybe this output, I'm not gonna give it that same threshold. Okay, because outputs, it really depends. Okay, the only thing is that I want to care about the input peaks, not the output peaks. So maybe I'll just divide this by 10 or whatever. Why is that so? Only input peaks are used to filter. Okay, meaning to say, like, even if the output, if the output is something like this purple purple column here. It's very small, but because the peak here is so high, and yet it results in a very small output, it means that there's a low gain here. There's low gain, and that is data you want to capture. Why? Because the input peak is very high compared to the rest of the peaks, and whatever the value of the output, it doesn't really matter. Okay? In terms of considering whether you want to take this data point. So even if your output is very small, you still want to take this data point. But if your input is small over here, you may not want to take this data point because it is small, relatively similar compared to the noise level. Okay, so let's do this. We have peak data input peaks. Okay. Okay, input peak magnitude and output peak magnitude. Okay, so you will have a vector of the input peak magnitude, and input peak magnitude and the input peak frequencies. That will be find peaks. Input magnitude. Okay, so you supply a vector of the input magnitude, you supply a vector of the frequencies. So you want to find peak using the input magnitude and the frequencies, these two vectors. Okay, what is your threshold? Instead of peak prominence, we are going to use minimum peak height. Again, because we are not doing in decibel anymore. So let's do a minimum peak height. Okay, I'm going to use minimum peak height. Okay, and of course we use the threshold input and output to control where the peaks are. Okay. And next thing, I also want to load the frequency and complex gain, which is this min peak height. Okay, then I'll have this next part actually tells me, where do I want to capture the frequency response data. So I will have this thing called input peak index. Okay, input peak index to store where I want all these peaks. Okay, so this is based on input magnitude, minimum peak height, and the threshold of the input. Then you have the input peaks and the output peaks. Yeah, and the peak frequencies. Okay, all this is the same as before. Complex peaks equals output over input. Okay, peak data dot peak frequency CSV equals to peak frequencies, and peak data complex gain CSV equals to complex gain. I think also sort of explained this peak finder code before in a few videos prior, so I'll not be going through those again. Next thing I want to do is to print the results. And I'll say this use clear figure to clear the figures. So I will use again minimum peak height as the metric of measure, and just doing find peaks will actually plot the graph out for us. All right. I can put a hold off over here, and let's do, instead of using peak finder, let's do linear peak finder. Then you should see the things slightly different. Okay, says cannot find. Oh, okay. The capital F is needed there. I'm suspecting there's some bugs, but okay. Now you can see. Alright, this is much better. Okay, so you can see that the peaks that we want, at least when we don't use decibels, we want the very high, the highest peaks. Okay, we don't exactly want the peaks that over here because they're very similar to the noise level. So we'll just discard this junk data. All of the data here is what we will take, and it won't be like every single data that we have, but only certain bits of data. And it's kind of funny. I can't. Yeah. I think there are like bits of data that I'm missing for some reason. But okay, never mind. We'll see where this is going. Okay. Alright, so let's see. All your peak data is here. And let's check out the frequency response peaks. Okay, there are 16 peaks here. So this is a very clean data. We don't have 100 peaks to actually concern ourselves. Only 16. And these are the relevant peaks that are the highest. They are at least magnitude of half, compared to the mean, the highest peak frequency, or compared to the peak with the highest magnitude. Okay, so these are the relevant peaks. So again, I'm only taking my frequency response data at places where the input peaks are high enough, so that there's a high signal to noise ratio. And how I determine that is to take the maximum peak reading for this, and I divide it by 2, and that is so-called my tolerance threshold for frequency response data. And that will help to supply us with a very clean data. Okay. Anything else we may not want to be using as frequency response data. Now, what do we have here? We have peak frequencies, which is over here. We can actually copy and paste this into a CSV file. And we have a complex gain thing here. So let's make a CSV file. But okay, maybe we'll do that next time. Yeah, but I hope I'm getting my point across that when we want to consider frequency response data, you want to consider points where the input frequency is, you want to only consider frequencies where the you only want to consider points, or you only want to consider input frequencies where the magnitude at those frequencies is much higher than the noise. And how I determine the threshold is to take the maximum input frequency and I divide it by 2, and that's how I determine, these are places where I have high signal to noise ratio. Therefore, I will only choose these points to consider my input. Of course, you can set your threshold a little bit lower if you want, and then of course you'll get more data points. And it all depends, okay? Whether you think there's a high signal to noise ratio over there. If it is so, then why not? Okay. Okay, let me close that. I don't know where that came from. Alright, so I mean, we can actually can see whether the signal to noise ratio is good. I mean, you can actually take some of these peaks as well. You can see that even here, the signal to noise ratio is pretty good. You can see the background noise is maybe all of these points. Yeah, you can see background noise over here. This is the background noise, maybe 5 times 10 to the minus 4. So there's very low background noise. Okay. Okay, that's very low background noise. Yeah, maybe you can set your peak tolerance to be a little bit lower, and then we can actually capture more of the data. So instead of divide by 2, maybe you can divide by 4. Yeah. Okay, maybe this is really up to you to adjust how sensitive you want it to be. Okay, and if you make it more sensitive, you're going to get more peak data. Now there are 57 frequencies you can actually get your data at. And take a look here. I hope you get the rationale, but yeah, this one will let you get even more pieces of data. And I think that is completely doable. It's yeah. Alright, so I think next I'm gonna stop here. I'm just gonna say, yeah, these are the collection of frequencies where I want to take my frequency response data. At other places I don't really want to bother. Okay? Because over here maybe the signal to noise ratio is not as good. Okay, so this one's cutting it is pretty good already. So yeah. let's see how to develop a transfer function from there on next. Okay, so see you next time.